Look up at the night sky, really look at it, and tell me what you see. A scattering of stars, a distant galaxy, maybe just the quiet, endless dark. But what if I told you that every pinprick of light out there, every swirling cosmic structure, holds a story far more incredible than we ever imagined? The universe isn't just vast, it's alive with motion, with birth and death on scales so enormous they defy human comprehension. Take the Hubble Deep Field image, for example, a tiny patch of sky no bigger than a grain of sand held at arm's length, yet packed with thousands of galaxies, each one a sprawling island of stars. How did they get there? Why do some galaxies spiral gracefully while others collide in violent, dazzling explosions? And what invisible forces sculpted them over billions of years? These aren't just poetic questions, they're the heart of some of the most profound mysteries in science. For centuries, we've pieced together theories, each one a stepping stone toward understanding the cosmos' grand design. But here's the thrilling part. We're standing at a turning point. Right now, 32 dynamic theories are reshaping how we see everything from the smallest particles to the largest galactic superclusters. Some suggest wild, untested ideas, cosmic filaments acting like rivers of dark matter, or black holes seeding new stars instead of devouring them. Others challenge the very laws we thought governed reality. And every single one of them could rewrite the story of how our universe came to be. So buckle up, because today we're diving headfirst into these mysteries. We'll explore how galaxies are born, why they evolve in such stunning variety, and what fate ultimately awaits them. Along the way, we'll uncover the hidden forces that weave the fabric of space itself, forces that might hold the key to our own existence. This isn't just a journey through science, it's a voyage into the unknown, where every discovery feels like unraveling a piece of the universe's best-kept secrets. By the end, you won't just see the night sky differently, you'll feel it. So let's begin. The Big Bang, it's the story we all know. A single, unimaginably hot and dense point erupting into everything we see today. But what if that's just the opening scene of a much grander epic? Picture this. In less than a blink of cosmic time, the universe expanded from smaller than an atom to the size of a galaxy. Matter, energy, even the laws of physics themselves were forged in those first chaotic moments. Yet for all its brilliance, the Big Bang leaves us with lingering questions. Why is the universe so perfectly balanced, as if fine-tuned for galaxies to form? How did tiny ripples in that primordial fireball grow into the vast webs of galaxies we see now? This is where things get even more fascinating. Some scientists argue that the Big Bang wasn't the true beginning, just a dramatic turning point in an older, deeper cycle. Take cosmic inflation, for example. This theory suggests that before the Big Bang, space itself underwent a runaway expansion, stretching quantum fluctuations into the seeds of future galaxies. Then there are cyclic models, which propose that our universe is caught in an endless loop of expansion and contraction, like a cosmic heartbeat. Each bounce could rewrite the rules, creating entirely new conditions for stars and galaxies to arise. But here's the real twist. None of these theories fully explain why galaxies look the way they do today. Why do some resemble spinning pinwheels while others are shapeless giants? That's where an invisible player steps in: dark matter. This mysterious substance doesn't just lurk in the shadows. It sculpts the cosmos, pulling galaxies into shape and weaving them into vast, luminous networks. Without it, stars might never have clumped together, and galactic spirals might never have spun into existence. Yet dark matter refuses to reveal its true nature, leaving us with a puzzle that could redefine our understanding of the universe's blueprint. So while the Big Bang gives us a starting point, the real story is far from over. It's a tale of hidden forces, cosmic rebirth, and questions that push the boundaries of imagination. And as we'll soon see, the answers might lie in the darkest corners of space where the universe's greatest secrets are waiting to be uncovered. Imagine building a city without ever seeing the blueprint. That's essentially what the universe has been doing with dark matter. This invisible substance doesn't just exist, it dominates the cosmos, outnumbering ordinary matter 5-1. Yet it leaves no trace, no light, no radiation, nothing but its gravitational fingerprint. The discovery of dark matter reads like a scientific detective story. In the 1970s, astronomer Vera Rubin noticed something bizarre. Stars at the edges of galaxies were orbiting just as fast as those near the center, defying Newton's laws. The only explanation, an enormous halo of unseen matter, gripping stars like an invisible hand. Today, supercomputer simulations reveal dark matter's grand design, a vast, intricate web stretching across the universe. Picture threads of spider silk, but on a cosmic scale, with galaxies clustered like dewdrops at the intersections. These filaments guide everything, funneling gas and stars into the majestic spirals and ellipticals we observe. Without dark matter's scaffolding, the universe might have remained a featureless sea of hydrogen. Yet for all its influence, we still don't know what it is. Some scientists hunt for WIMP, weakly interacting massive particles, hypothetical entities that could solve the puzzle. Others propose actions, ghostly particles born in the early universe. But there's a radical alternative. What if dark matter doesn't exist at all? Modified Newtonian dynamics, or MUND, suggests gravity itself behaves differently at galactic scales. It's a compelling idea, yet it struggles to explain the bullet cluster, two galaxy clusters colliding, with their dark matter seemingly left behind like a shadow. The debate rages on, but one thing's clear: dark matter is the universe's master sculptor, shaping galaxies with silent precision. And if we're wrong, if gravity itself is the illusion, then everything we know about cosmic structure could unravel. Which begs the question, what other invisible forces are lurking in the void, waiting to rewrite the rules? If dark matter is the invisible hand shaping galaxies, then dark energy is the silent force stretching the very fabric of space itself. In the late 1990s, astronomers made a discovery so shocking it upended cosmology. The universe isn't just expanding, it's accelerating. Distant supernova, those cosmic lighthouses, were dimmer than expected, as if something were pushing them farther away at breakneck speed. That something, dark energy, a mysterious pressure filling the void, accounting for nearly 70% of the universe's total energy. Einstein might have glimpsed it first. His cosmological constant, a mathematical fudge factor he later called his biggest blunder, described a repulsive force balancing gravity to keep the universe static. Turns out he wasn't entirely wrong. Today, the cosmological constant is a leading explanation for dark energy, a steady, unchanging presence woven into space itself. But there's a twist. What if dark energy isn't constant at all? Some theories propose quintessence, a dynamic field that evolves over time, growing stronger or weaker like the ebb and flow of a cosmic tide. The implications are staggering. If dark energy intensifies, it could trigger a big rip, where galaxies, stars, even atoms are torn apart in a final, violent expansion. Alternatively, it might fade, allowing gravity to reverse the universe's fate in a big crunch. Or perhaps space will continue stretching indefinitely, leaving galaxies isolated in an ever-cooling void. Supernova data offers clues, but the puzzle remains. Why does dark energy dominate now after billions of years of gravity's reign? Is it a fundamental property of space or a sign of new physics waiting to be discovered? One thing's certain, the universe's fate hinges on this enigmatic force, and we're only beginning to grasp its power. Think of blowing up a balloon, not just gently, but in a single, sudden burst that stretches it from a speck to a beach ball in less than a second. That's cosmic inflation, the universe's most dramatic growth spurt. In the tiniest fraction of a moment after the Big Bang, space itself expanded faster than the speed of light, doubling in size over and over again like a runaway chain reaction. This wasn't just expansion, it was exponential, transforming a subatomic flicker into a cosmos vast enough to eventually birth galaxies. Why does this matter? Inflation solves two of the universe's most baffling riddles: uniformity and flatness. Look at the cosmic microwave background, the afterglow of the Big Bang, and you'll see a near-perfect temperature spread across the sky, as if someone smoothed out the cosmos with a cosmic iron. Without inflation, regions now billions of light-years apart could never have reached equilibrium, yet they're almost identical. Inflation stretched those tiny quantum fluctuations into the seeds of galaxies, weaving a tapestry of matter so precise it defies coincidence. But not everyone agrees. The bouncing universe model suggests a cyclical cosmos where each Big Bang is preceded by a collapse, a cosmic reset button. Imagine a slinky falling and rebounding, each bounce creating new conditions for galaxies to form. It's an elegant idea, but inflation has something bouncing theories lack: evidence. The cosmic microwave background's faint temperature variations match inflation's predictions like a fingerprint, while gravitational wave detections could soon seal the deal. Yet the most thrilling question remains: how did this explosive growth shape the galaxies we see today? Those quantum ripples stretched by inflation didn't just fade, they became gravitational wells, pulling in gas and dark matter until stars ignited and galactic spirals took shape. Without that split-second surge, the universe might have remained a formless void. So next time you gaze at the night sky, remember, every galaxy, every star, even you, owe your existence to the universe's wildest growth spurt. A moment so brief, it's almost impossible to fathom, but whose echoes still shape everything we know. Picture a pond on a perfectly still morning so calm, its surface is like glass. Then, a single pebble drops in. Tiny ripples spread outward, growing, intersecting, creating patterns in the water. Now imagine that pond is the newborn universe, and those ripples are quantum fluctuations, tiny, random variations in energy and density, smaller than an atom. In the first trillionth of a second after the Big Bang, these fluctuations were frozen into place by cosmic inflation, stretched across light years like fingerprints pressed into the fabric of space itself. These minuscule wrinkles became the universe's blueprint. Where the ripples were slightly denser, gravity got to work, pulling in dark matter and gas over billions of years until galaxies blossomed like flowers in a cosmic garden. The proof: look at the cosmic microwave background, the afterglow of the Big Bang, where those primordial ripples appear as faint temperature variations, a snapshot of the universe's infancy. It's as if we're staring at the seeds of everything, the Milky Way, Andromeda, even the vast voids between them, all encoded in those subtle fluctuations. But there's more to the story. Enter baryonic acoustic oscillations, sound waves that race through the early universe's soupy plasma, like echoes of a cosmic drumbeat. When the universe cooled enough for atoms to form, these waves froze in place, leaving a signature. Galaxies today are slightly more likely to be separated by about 500 million light-years, the distance those sound waves traveled before fading. It's a ghostly rhythm, a heartbeat from the dawn of time still shaping where galaxies cluster. Yet for all this order, the universe has a violent side. Just as those early ripples birthed galaxies, they also set the stage for a darker phenomenon, galactic cannibalism. When galaxies grow too close, gravity doesn't just nudge them, it tears them apart, merging them into something new. Our own Milky Way is no innocent bystander. It's currently digesting smaller galaxies, their stars strewn across our skies like cosmic crumbs. And in the distant future, it will collide with Andromeda, a fiery dance that reshapes both into a single, colossal galaxy. From quantum whispers to celestial collisions, the universe's story is written in gravity's relentless pull, a tale where creation and destruction are two sides of the same cosmic coin. Galaxies aren't the solitary giants we often imagine. They're more like cosmic predators, growing by devouring their smaller neighbors in a process as violent as it is beautiful. Take the Milky Way. Right now, it's tearing apart the Sagittarius dwarf spheroidal galaxy, stretching its stars into a shimmering river across our night sky. This isn't some rare event, it's how galaxies evolve. Nearly a third of all galaxies show signs of past mergers, their structures twisted by gravitational encounters that rewrite their shapes forever. The most dramatic example looms in our future, the Milky Way and Andromeda, two spiral galaxies currently racing toward each other at 200,000 miles per hour. Simulations show their first close pass in about 4 billion years, not a head-on crash, but a gravitational tango that will stretch both galaxies into bizarre, elongated shapes. Stars won't collide, space is too vast, but their orbits will be flung into chaos. Gas clouds will compress, igniting fireworks of new star formation as the galaxies swing past each other again and again, eventually merging into a single, bloated elliptical galaxy some dub Milkdromeda. These collisions aren't just destructive, they're creative. When galaxies merge, their interstellar gas slams together, triggering bursts of star formation so intense they're called starburst galaxies. The antennae galaxies, locked in a slow-motion collision, are birthing stars at a rate 20 times faster than the Milky Way, their spiral arms shredded into luminous tendrils. Yet mergers also have a dark side. Supermassive black holes at their cores eventually spiral together, releasing gravitational waves that ripple through space-time itself. What does this mean for the stars caught in these cosmic upheavals? Most will survive, tossed into new orbits like leaves in a storm. But their night skies will transform. Where once they saw a single galactic disk, they'll witness a swirling chaos of stars from two merged civilizations. Imagine standing on a planet in that far future, looking up at a sky ablaze with unfamiliar constellations, the legacy of a collision written in starlight. This cycle of destruction and rebirth isn't unique to our corner of the cosmos. From the mice galaxies with their long, luminous tails to the penguin and egg galaxy locked in a gravitational embrace, these mergers are universal architects, sculpting the diverse galaxy shapes we see today. And just as stars are born from the wreckage of these collisions, their deaths will seed the next generation, a cycle as old as the universe itself. Deep within the swirling clouds of cosmic dust and gas, hidden from plain sight, lies one of the universe's most breathtaking spectacles, stellar nurseries. These colossal nebulae, like the Orion Nebula, glow with the light of newborn stars, their vibrant hues painting the darkness like celestial watercolors. But behind that beauty lies an epic struggle: gravity against pressure, chaos against creation. Take the Orion Nebula, just 1,500 light-years away. What looks like a faint smudge to the naked eye is, in reality, a turbulent cauldron of gas and dust, dense enough to blot out starlight. Yet within those dark pockets, something extraordinary happens. When a cloud grows massive enough, its own gravity begins to overwhelm the outward pressure of the gas. This tipping point, called Jean's instability, triggers collapse slowly at first, then faster, until the core becomes so hot and dense that hydrogen atoms fuse into helium. In that moment, a star is born, igniting like a cosmic match in the dark. Carl Sagan once described star formation as the universe becoming aware of itself. And it's hard not to feel that awe when you realize that every shining point in our night sky began this way, condensing from an anonymous cloud into a radiant furnace of light. But these young stars don't just flicker quietly into existence, they reshape their surroundings with violent energy. Their fierce stellar winds carve cavities in the nebula, while their ultraviolet radiation ionizes the gas, making it glow in brilliant reds and blues. Yet the most surprising twist, these stellar newborns don't stay put. Over millions of years, they drift away from their birthplaces, scattering across the galaxy like seeds in the wind. Some will join the spiral arms, others may cluster together in dazzling groups, but all will carry with them the chemical legacy of their origins, heavy elements forged in the hearts of stars that came before them. So the next time you gaze at Orion's belt, remember, you're not just seeing stars, you're witnessing a cosmic cradle where the next generation of suns is taking its first breath. Some stars don't fade quietly into the cosmic night, they go out with a bang so colossal it can outshine entire galaxies. Supernova are the universe's ultimate recyclers, forging the very elements that make up our bodies, our planet, and everything we know. Take the Crab Nebula, a tangled web of gas and dust glowing 11,000 light-years away. What we see today is the aftermath of a star's self-destruction, a cataclysm so bright it was recorded by Chinese astronomers in the year 1054 as a guest star visible even in daylight. But not all supernovae are created equal. Core collapse supernovae happen when massive stars, at least 8 times heavier than our Sun, exhaust their nuclear fuel. Without the outward pressure of fusion to balance gravity's relentless pull, the star's core collapses in less than a second, triggering a shock wave that blasts the outer layers into space at millions of miles per hour. The core, it crumples into a neutron star or black hole, so dense a teaspoon of its material would weigh 1 billion tons on Earth. These explosions are element factories. Carbon, oxygen, iron, even gold are forged in their fury and scattered like cosmic confetti, seeding future generations of stars and planets. Then there's Type Ia supernova, the universe's standard candles. These occur when a white dwarf, the dense remnant of a sun-like star, steals too much material from a companion, crossing a critical mass threshold. The result is a runaway nuclear explosion so uniform in brightness, astronomers use them to measure cosmic distances. It was Type Ia supernova that revealed dark energy's existence, proving the universe's expansion is accelerating. But supernovae aren't just distant spectacles, they're potential threats. A nearby event within 50 light-years could bathe Earth in deadly radiation, stripping the ozone layer and triggering mass extinctions. Fortunately, the closest candidate, Betelgeuse, sits safely at 640 light-years away. Yet even in death, these stars shape galactic evolution. The shockwaves from supernova compress nearby gas clouds, triggering new star birth, while the heavy elements they spew enrich entire galaxies. And when the dust settles, sometimes all that remains is a black hole, a gravitational anchor that can shape the orbits of stars around it, slowly sculpting the galaxy itself. From destruction comes creation. Every atom in your body was once forged in the heart of a dying star, hurled across space by a supernova's fury. So the next time you look up at the night sky, remember, you're not just stardust. You're the legacy of cosmic violence, a testament to the universe's endless cycle of death and rebirth. At the heart of nearly every galaxy, including our own Milky Way, lurks a cosmic monster, a supermassive black hole, millions to billions of times heavier than our Sun. Sagittarius, a star, the one anchoring our galaxy, may seem quiet now, but don't let its stillness fool you. These gravitational giants aren't just passive voids, they're galactic engines, shaping the destiny of entire star systems around them. Picture an enormous whirlpool in space, where gas, dust, and even stars spiral inward, heating up to millions of degrees as they form a glowing disk of superheated plasma. This accretion disk doesn't just feed the black hole, it powers some of the universe's most energetic phenomena. When material gets too close, it doesn't just vanish. Some gets funneled into narrow jets shooting out at nearly the speed of light, stretching thousands of light years into space. These jets can carve through entire galaxies, heating interstellar gas so intensely it stifles star formation, effectively putting a cosmic brake on galactic growth. That's right, black holes don't just consume, they regulate. In galaxy clusters like Perseus, these jets blow enormous bubbles in the surrounding gas, preventing it from cooling and collapsing into new stars. It's a delicate balance: too much activity and the galaxy starves, too little and stars form unchecked, leading to runaway stellar populations. But here's where things get truly mind-bending. Some theories suggest black holes might be more than just gravity wells, they could be cosmic hard drives. The holographic principle proposes that all the information swallowed by a black hole isn't lost but encoded on its event horizon, like a three-dimensional movie projected onto a two-dimensional surface. Imagine every star, planet, or atom ever consumed being stored as infinitesimally tiny pixels on the black hole's boundary. If true, it could mean reality itself has a hidden layer, a deeper structure where information is fundamental, not matter. Which leads to the ultimate question: what happens beyond the event horizon? Could black holes be gateways, wormholes twisting space-time so severely they connect to other universes? While Einstein's equations allow for such tunnels, the crushing tidal forces and quantum mysteries make survival unlikely. Yet some models, like black hole cosmology, speculate that our own universe might have been born inside one. Picture a black hole in some higher dimensional space, its interior stretching into an entire cosmos of its own, a cosmic Russian nesting doll of realities. One thing's certain: black holes aren't the end of the story. They're the architects of galaxies, the keepers of spacetime's deepest secrets, and perhaps the key to understanding reality itself. And as we peer deeper into their mysteries, we might just find that the universe's darkest corners hold its brightest revelations. What if our universe isn't the only one? Imagine a cosmic foam where each bubble is an entire universe with its own laws of physics, its own stars, its own version of reality, some with gravity so strong, galaxies crumble instantly, others where time flows backward. This isn't science fiction, it's the multiverse theory, a radical idea gaining traction among cosmologists. The concept springs from eternal inflation, an extension of the Big Bang's explosive growth. While our universe stopped inflating, forming galaxies and stars, other regions of space might still be stretching exponentially, spawning new bubble universes endlessly, like a cosmic popcorn maker, kernels of reality bursting into existence at random. String theory adds another layer to this mind-bending landscape. It suggests that the fundamental constants of nature, the strength of gravity, the mass of an electron, aren't fixed but determined by how tiny, vibrating strings fold into higher dimensions. Each unique configuration could birth a universe with entirely different physics. Picture a cosmic dice roll. In one universe, atoms might never bond, leaving no chemistry for life. In another, dark energy dominates so fiercely that galaxies are ripped apart before they form. Our universe, just one lucky ticket in an infinite lottery where the conditions happen to allow galaxies, stars, and us. But is this science or philosophy? Critics argue the multiverse is untestable, a convenient way to explain our universe's fine-tuning without evidence. After all, if every possible reality exists, how do we prove ours isn't just statistical noise? Supporters counter that cosmic inflation's fingerprints are already visible in the microwave background, and future gravitational wave detectors might uncover signatures of collisions with other bubble universes. The debate cuts to the heart of what science can and should explain. Now consider the staggering implication for life. If the multiverse is real, then somewhere out there, countless versions of Earth might exist, each with histories slightly or wildly different from our own. But here's the twist: most of those universes would be barren, their laws too hostile for even atoms to stabilize. That raises a haunting question. Are we here because the universe conspired to allow life, or are we simply the ones who got lucky, gazing out from a rare cosmic oasis where the numbers lined up just right? The answer could redefine not just our place in the cosmos, but the very nature of existence itself. The universe is ancient beyond comprehension, 13.8 billion years old, with hundreds of billions of galaxies, each hosting billions of stars. Statistically, life should be everywhere. So where is everybody? This is the Fermi Paradox, a haunting question that's puzzled scientists since physicist Enrico Fermi first posed it over lunch in 1950. If the cosmos is so vast and so old, why haven't we found a single trace of extraterrestrial intelligence? The silence is deafening. One answer might lie in the Drake equation, a framework for estimating the number of civilizations in our galaxy. It considers factors like star formation rates, planets' inhabitable zones, and the likelihood of life emerging. Plug in optimistic numbers, and the Milky Way should be buzzing with activity. But reality tells a different story. This gap between expectation and observation has spawned chilling theories like the Great Filter. Imagine an invisible barrier, a cosmic bottleneck that prevents life from advancing beyond a certain point. It could lurk in our past. Perhaps the leap from simple cells to complex life is astronomically rare. Or worse, it might await us in the future, a catastrophic event like runaway AI or self-destructive technology that dooms all advanced civilizations before they can colonize the stars. Then there's the zoo hypothesis, the idea that aliens exist but deliberately avoid us, observing humanity like animals in a galactic nature preserve. It's a tantalizing thought, but it raises unsettling questions. Who are the zookeepers, and why would they stay hidden? Others suggest we're simply too early, that life's golden age lies billions of years in the future, when the universe cools enough for red dwarf stars to dominate. Or maybe we're looking for signals all wrong. What if advanced civilizations communicate via neutrino beams or dark matter, technologies we can't yet detect? This leads us to the anthropic principle, a humbling perspective. The universe appears fine-tuned for life because we're here to observe it. If conditions were even slightly different, if gravity were stronger or the cosmological constant smaller, galaxies, stars, and life might never have formed. So while the cosmos seems empty, it might just be that intelligent life is vanishingly rare, or that we're the first to rise. The silence isn't just a puzzle, it's a mirror, forcing us to confront our own fragility in an indifferent universe. And as we keep listening, the question remains, are we alone, or is something, or someone waiting just beyond the edge of our perception? Consider the gravitational constant, the precise number that determines how strongly objects attract each other. If it were just slightly stronger, stars would burn too hot and fast, snuffing out life before it could begin. A fraction weaker, and matter might never have clumped into galaxies at all. This isn't just a lucky break, it's one of dozens of fundamental constants that seem eerily fine-tuned for life's existence. The speed of light, the strength of nuclear forces, even the amount of dark energy, each one balanced on a razor's edge, as if the universe were calibrated for our arrival. This observation leads us to the anthropic principle, a concept as profound as it is contentious. The weak version states simply, we observe the universe the way it is because we couldn't exist otherwise. It's a cosmic selection bias, like a fish marveling at how perfectly water suits its gills. But the strong anthropic principle goes further, suggesting the universe must have properties that allow life to emerge, almost as if it were designed to do so. Proponents point to the mathematical precision of these constants, arguing that the odds of such perfect alignment by chance are astronomically low. Critics counter with the multiverse. If infinite universes exist, each with random physical laws, then statistically, a handful would inevitably hit the jackpot, conditions just right for life. We'd find ourselves in one of those lucky few, no design required. It's like buying 1,000,000 lottery tickets. Even with terrible odds, someone wins eventually. The catch, this theory leans on unobservable alternate realities, leaving some scientists uneasy. Could the multiverse be a convenient escape hatch, or does it genuinely explain the fine-tuning mystery? Yet there's another layer to this puzzle: chaos. The universe isn't a static, perfectly tuned machine. It's a dynamic, often violent place where randomness plays a starring role. Supernovas scatter heavy elements, asteroid impacts reset evolutionary paths, and galactic collisions reshape star systems. Life didn't emerge despite this chaos, it emerged because of it. The same turbulence that threatens existence also creates the diversity and complexity that make life possible. So is the universe fine-tuned, or are we just survivors of cosmic roulette? The answer might lie somewhere in between, a dance of precise constants and chaotic opportunity, where the conditions for life are rare but not miraculous. And as we unravel this balance, we're left with a humbling thought. Perhaps the universe isn't made for us, but we are undeniably made from it. A butterfly flaps its wings in Brazil, so the saying goes, and weeks later a tornado rips through Texas. This poetic idea, Lorenz's butterfly effect, captures how tiny, seemingly insignificant changes can cascade into enormous consequences. Now scale that up to cosmic proportions. The universe itself might be the ultimate example of chaos theory in action, where microscopic quantum fluctuations in the first moments of existence snowballed into the vast galactic structures we see today. Picture the newborn universe, a seething sea of energy where particles flicker in and out of existence, governed by quantum randomness. These fleeting fluctuations, smaller than atoms, were stretched to astronomical scales during cosmic inflation, frozen into the fabric of space-time like cosmic fingerprints. Fast forward billions of years, and those same minuscule ripples became gravitational seeds, regions where matter clumped slightly denser, pulling in gas and dark matter until galaxies blossomed. The Milky Way, Andromeda, even the sprawling web of galaxy clusters, all trace back to those quantum whispers. The universe's grand architecture, in other words, might be built on a foundation of chaos. But here's the twist. If the universe is so sensitive to initial conditions, does that mean its structure is fundamentally unpredictable? After all, we can't rewind time to measure those first quantum fluctuations with infinite precision. Some scientists argue that cosmic evolution is deterministic, that if we knew every variable, we could chart the universe's fate with perfect accuracy. Others see true randomness in quantum mechanics, suggesting the cosmos is an ever-branching tree of possibilities. This uncertainty leads us to an even wilder idea. What if the universe isn't just shaped by chaos, but is itself a kind of hologram? The holographic principle suggests that all the information in our three-dimensional reality might be encoded on a two-dimensional surface, like a cosmic projector screen. In this view, those early quantum fluctuations weren't just random noise, they were pixels in a deeper, hidden code, a blueprint for space-time itself. It's as if the universe is both the painting and the canvas, with every galaxy, every star, even us, emerging from a shadow play of information. So the next time you gaze at the night sky, remember, the majestic spiral of a galaxy or the void between stars might all trace back to a quantum flutter, a cosmic butterfly whose wings beat 13 billion years ago, shaping everything we know. What if everything you see, the stars, galaxies, even the screen in front of you, is just a shadow, a projection of information encoded on a two-dimensional surface at the edge of the universe? This isn't science fiction, it's the holographic principle, one of the most radical ideas in modern physics. The theory traces back to an unexpected source: black holes. In the 1970s, physicist Jacob Bekenstein discovered something startling. A black hole's entropy, its measure of disorder, isn't proportional to its volume, as you'd expect, but to the area of its event horizon. It's as if all the information about what falls into a black hole isn't lost inside but smeared across its surface like ink on a cosmic parchment. This led to a staggering realization. If a three-dimensional black hole's information can be encoded in two dimensions, maybe our entire universe works the same way. Enter the AD/S/CFT correspondence, a mathematical framework suggesting our four-dimensional spacetime, three of space, one of time, could be a hologram projected from a lower dimensional reality. Picture a movie screen. The flat surface contains all the data needed to create the illusion of depth, motion, even time. In this view, the universe isn't just built on particles and forces. It's fundamentally made of information, with every event, every interaction, just a pixel in a vast cosmic code. But how could this possibly be tested? Surprisingly, there are clues. Quantum entanglement, the eerie connection between particles across vast distances, might be the glue holding the hologram together. Experiments show entangled particles behave as if they're linked by hidden threads, a phenomenon that aligns eerily with the holographic principle's idea of surface-level information manifesting as three-dimensional reality. Even gravity, the force that shapes galaxies, could emerge from this informational substrate, like waves rising from the ocean's deeper currents. Now, here's the mind-bending twist. If reality is a hologram, what does that make time? In most physics equations, time is just another dimension, but holography suggests it might be an emergent property, a side effect of how information organizes itself at the universe's boundary. Think of a flipbook. The illusion of motion comes from static pages changing incrementally. Similarly, time's flow could be our perception of information updating frame by frame on the cosmic screen. This raises a haunting question. Is the universe fundamentally digital? Are we living in a cosmic simulation where the laws of physics are just the programming code? While some dismiss this as philosophy, others point to the holographic principle's mathematical rigor. After all, if spacetime is pixelated at the Planck scale, the smallest possible unit, then reality might literally be built from bits. It's a humbling thought. The galaxies we admire, the stars we study, even our own consciousness, could be the output of an unimaginable computation happening at the edge of everything we know. And if that's true, then time itself, the force driving cosmic evolution, might not be a river but a script unfolding line by line on the universe's hidden surface. Time flows forward like an unstoppable river, carrying the universe from order to chaos. This is the arrow of time, a fundamental law of nature we take for granted every day. Eggs crack but never uncrack themselves, ice melts but doesn't refreeze spontaneously, and stars burn out but never reignite. Underlying all of this is the second law of thermodynamics, entropy. The measure of disorder in a system always increases. But what does this mean for the cosmos? Imagine the early universe as a perfectly smooth, high-energy soup, a state of exquisite order. Over billions of years, gravity amplified tiny fluctuations, sculpting galaxies and stars. Yet with each transformation, the universe became more disordered. Even as galaxies form, they radiate heat into space, spreading energy outward in a way that can never be fully recovered. The universe isn't just expanding, it's unraveling. But here's where things get strange. If entropy always rises, why did the universe start in such an ordered state? Some theories suggest our cosmos began as a rare statistical fluctuation, a random dip into low entropy against a backdrop of chaos. This idea leads to one of the most bizarre thought experiments in physics, Boltzmann brains. Named after physicist Ludwig Boltzmann, it proposes that in an infinite, chaotic universe, random fluctuations could occasionally assemble a fully formed, self-aware mind, complete with false memories of a past that never existed. These disembodied observers would arise from the void, convinced they're living in an orderly universe like ours, only to dissolve back into chaos moments later. It's an unsettling notion, implying that statistically, there should be far more Boltzmann brains than real, evolved beings like us. So why aren't we one of them? The answer might lie in cosmic cycles. Some models propose that entropy doesn't spell the universe's end, but sets the stage for rebirth. In a cyclic universe, each Big Bang is preceded by a big crunch, where matter and energy collapse into a singularity before rebounding. Entropy resets in each cycle, offering a fresh canvas for new galaxies to form. String theory even suggests our universe could be a four-dimensional brain, colliding with another in higher dimensional space, igniting expansion anew. These theories offer an elegant solution. Time's arrow isn't a one-way street but part of an endless loop where destruction fuels creation. Yet the mystery deepens when we consider black holes' cosmic entropy factories. Their event horizons trap so much disorder that physicist Stephen Hawking once argued they might hold the key to understanding time itself. As black holes evaporate over eons, leaking Hawking radiation, they could be the universe's way of balancing the books, redistributing entropy across the cosmic ledger. And if the holographic principle is correct, this dance of disorder might all be encoded on the universe's boundary, a hidden ledger where time's arrow is just another entry. From the inevitability of entropy to the eerie possibility of Boltzmann brains, the universe's fate is intertwined with the nature of time itself. Whether it's a one-way slide into chaos or a chapter in an infinite cycle, one thing is certain: the cosmos is far stranger and more wondrous than we ever imagined. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic saga? Enter conformal cyclic cosmology, a mind-bending theory proposed by physicist Roger Penrose. Picture this: instead of a one-time explosion, our universe undergoes infinite cycles, each ending not with a whimper, but a transformation. As space expands to near nothingness over trillions of years, galaxies, black holes, even particles themselves dissolve into pure energy. But here's the twist. That sparse, uniform energy state eerily resembles the ultra-smooth conditions of the Big Bang's starting point. In this view, the universe doesn't truly end. It resets, stretching and smoothing until a new cycle ignites, birthing fresh galaxies from the ashes of the old. Penrose's radical idea finds potential support in Hawking points, strange, circular patterns in the cosmic microwave background. These faint imprints might be the gravitational echoes of supermassive black holes from a previous universe, their final bursts of radiation etched onto the newborn cosmos like cosmic graffiti. It's a controversial claim, but if verified, it would mean our universe carries scars from an era before time as we know it. Yet cyclic models aren't all the same. The classic Big Crunch scenario, where gravity eventually reverses the universe's expansion, collapsing everything back into a singularity, offers a darker vision. Imagine all galaxies rushing toward each other, space itself crumpling like paper, until the cosmos becomes a superheated seed ready to explode anew. But observations of dark energies accelerating expansion have dimmed this theory's appeal. Unless dark energy weakens or reverses, the universe may face a colder fate, heat death. In this scenario, expansion never stops. Stars burn out, black holes evaporate, and space becomes an endless, lifeless void, a frozen graveyard where even time loses meaning. Quantum gravity could hold the key to these cosmic cycles. String theory suggests higher dimensional branes might collide periodically, igniting new bangs without singularities. Loop quantum gravity, meanwhile, proposes that spacetime's granular structure prevents total collapse. Like a cosmic trampoline, the universe rebounds when compressed beyond a certain point. These theories hint at a profound truth. The cycle of destruction and creation might be written into the fabric of reality itself. From Penrose's recycled cosmos to the chilling silence of heat death, the universe's fate hinges on forces we're only beginning to understand. One thing's certain, whether it's a fiery rebirth or an eternal fade, the story of the cosmos is far from over. Einstein's general relativity paints gravity as the curvature of spacetime, a smooth, geometric dance where planets and stars warp the cosmic fabric. Meanwhile, quantum mechanics reveals a subatomic world of flickering particles and unpredictable probabilities, where nothing is certain and everything exists in a haze of possibility. These two pillars of modern physics work flawlessly in their own domains, but when they collide, like at the center of a black hole or the instant of the Big Bang, the math breaks down into nonsense. The quest to unite them, to find a theory of quantum gravity, isn't just academic. It's the key to unlocking the universe's deepest secrets. Take loop quantum gravity, one of the boldest attempts to reconcile these worlds. Picture spacetime not as a continuous sheet, but as a tapestry woven from tiny, indivisible threads, loops so small, 1 trillion could fit across a single atom. These loops intersect and braid, creating the fabric of reality itself. In this view, the Big Bang wasn't a singularity of infinite density, but a quantum bounce, where a previous universe collapsed to a point before rebounding like a spring. It's a radical idea, but one that elegantly sidesteps the mathematical nightmares of infinity. Then there's string theory, the glamorous rival. Here, particles aren't dots but vibrating strings, each oscillation producing a different particle, like notes on a cosmic guitar. To make the math work, strings require extra dimensions, curled up so tightly we'll never perceive them. Some versions even suggest our universe is a 4-dimensional brane, floating in a higher dimensional space, with gravity leaking in from neighboring realms. While critics argue string theory lacks testable predictions, its mathematical beauty keeps it in the race. But why does quantum gravity matter for the Big Bang? Without it, we hit a wall. General relativity predicts a singularity at time 0, a point where density becomes infinite and physics stops making sense. Quantum gravity could rewrite that story, revealing a moment of quantum foam where spacetime itself flickered in and out of existence. Some models suggest the Big Bang was less an explosion and more a phase transition, like water freezing into ice, marking the birth of time as we know it. This leads us to an even wilder possibility, the simulation hypothesis. If space-time is fundamentally pixelated, a network of loops or strings, could reality itself be a kind of computation? The idea isn't as far-fetched as it sounds. Just as a video game renders a seemingly continuous world from discrete code, the universe might emerge from underlying quantum bits. Physicists like James Gates have even found error-correcting codes, the same ones used in computer science, embedded in the equations of string theory. Coincidence or a clue? Whether loops, strings, or something stranger, the search for quantum gravity isn't just about equations. It's about understanding where the cosmos came from and whether the universe we see is the only one that exists. The answers, when they come, might rewrite not just physics but our very place in reality. What if your morning coffee, the stars above, even the thoughts swirling in your mind right now, aren't truly real? Simulation theory isn't just sci-fi fodder. It's a serious hypothesis gaining traction among scientists and philosophers. Oxford's Nick Bostrom frames it as a trilemma. At least one of these statements must be true. 1. Almost all civilizations self-destruct before reaching technological maturity. 2. Advanced civilizations lose interest in creating simulations of their ancestors. Or 3. We're almost certainly living in a simulation. Think about that for a moment. If even a single advanced civilization ever ran ancestor simulations, the number of simulated minds would dwarf biological ones, making it statistically likely you're one of them. The implications are staggering. If we're code in some vast computational matrix, the laws of physics might just be the rules of the program. Glitches could explain quantum weirdness, like particles being in two places at once until observed, as if the simulation renders reality only when needed to save processing power. Even the speed of light might be a built-in limit to prevent system overload. Some physicists take this further, pointing to the universe's mathematical precision, how fundamental constants align so perfectly, as if fine-tuned by a programmer. Others counter that evolution could favor universes capable of hosting life, no designer required. But here's the ethical quandary. If we're simulations, do our choices matter? Would discovering the truth collapse societal structures or inspire us to hack our reality? Elon Musk famously argued the odds we're in base reality are 1 in billions. Yet philosopher David Chalmers suggests even simulated lives have meaning. If you feel joy or love, does its origin change its value? This leads us to consciousness, the elephant in the cosmic room. Why does subjective experience exist at all? In a purely physical universe, shouldn't brains just process information without the glow of awareness? Some theorists propose consciousness is fundamental. Like space-time, perhaps the universe simulates itself into existence through observation. Others speculate that if we're in a simulation, our minds might be the only real things, with everything else rendered as needed. So, would you want to know the truth? Or is the mystery itself what makes existence beautiful? Whether we're stardust or strings of code, one thing's certain. The universe's greatest enigma might not be out there in the cosmos, but in the very nature of our perception. Consciousness might not be just a byproduct of the brain. It could be woven into the very fabric of reality. This is the bold claim of panpsychism, the idea that even the smallest particles possess some rudimentary form of awareness. Think of it like this: if the universe is built from fundamental building blocks, electrons, quarks, photons, why should consciousness emerge only when these particles arrange themselves in complex structures like brains? Maybe the capacity for experience isn't assembled. Maybe it's always been there, just in simpler forms. Nobel laureate Roger Penrose takes this even further. Along with anesthesiologist Stuart Hameroff, He proposes that consciousness arises from quantum processes in the brain's microtubules, tiny protein structures inside neurons. According to their theory, orchestrated objective reduction, these quantum vibrations don't just facilitate thought, they connect our minds to the universe's fundamental geometry. In other words, spacetime itself might have a form of proto-consciousness, and our awareness taps into that deeper layer of reality. It's a wild idea, but one that bridges the gap between quantum physics and subjective experience in a way traditional neuroscience hasn't. Then there's the observer effect in quantum mechanics, where particles seem to choose their state only when measured. Some interpretations, like the von Neumann-Wigner hypothesis, suggest consciousness collapses the quantum wave function, that reality remains in flux until a mind observes it. If true, the universe wouldn't just contain consciousness, it would depend on it to exist at all. Picture a cosmic game of Schrödinger's cat, where galaxies, stars, and even the laws of physics remain in superposition until some form of awareness, whether human, alien, or something stranger, locks them into place. But what if there's no observer? What if the universe is just nothing? Enter quantum fluctuations, where particles pop in and out of existence in empty space, borrowing energy from the void before vanishing again. This isn't just theoretical, it's measurable, as seen in the Casimir effect, where two metal plates in a vacuum are inexplicably pushed together by these ghostly particles. The implications are staggering. Even in total emptiness, there's activity, a seething potential for something to emerge. From panpsychism's conscious cosmos to the quantum foam of nothingness, the line between existence and observation blurs. Maybe the universe isn't just aware, maybe it's dreaming itself into being, one particle at a time. The universe has a funny way of playing tricks on us, especially when it comes to the very idea of nothingness. You might think empty space is just a void, a blank canvas where nothing happens, but the quantum world laughs at that assumption. In reality, so-called empty space is a seething, bubbling ocean of activity. Virtual particles, pairs of matter and antimatter, constantly pop into existence, borrowing energy from the vacuum before annihilating each other in a flash, all within fractions of a second. This isn't just theoretical, it's measurable with real-world consequences. Take the Casimir effect, one of the strangest demonstrations of quantum nothingness in action. Place two uncharged metal plates incredibly close together in a vacuum, and instead of just sitting there, they're inexplicably drawn toward each other. Why? Because the space outside the plates allows for more quantum fluctuations than the narrow gap between them. The sheer pressure of these ghostly particles pushing from the outside forces the plates together, proving that even in total emptiness, there's an underlying energy, zero-point energy, that never switches off. It's as if the universe refuses to sit still, even in its quietest moments. This raises a mind-bending possibility. Could the universe itself have been born from nothing? Some theories suggest that quantum fluctuations in a primordial vacuum could have sparked the Big Bang, a spontaneous eruption of spacetime from pure potential. Imagine a cosmic lottery where universes bubble up endlessly, each with its own laws of physics, most collapsing instantly, but every so often, one hits the jackpot, stabilizing into a reality like ours. If true, then nothingness isn't an end but a womb, constantly giving birth to new possibilities. Now flip the script. If black holes are cosmic vacuum cleaners, sucking matter into oblivion, could their opposites exist? Enter white holes, theoretical cosmic geysers where matter and energy explode outward, a one-way exit from some hidden dimension. While no white hole has ever been observed, some physicists speculate they could be the other end of a black hole's tunnel, spewing out what their dark counterparts consume. Others suggest they might be the remnants of a rebounding universe, a Big Bang in reverse. Whether white holes are real or just mathematical mirages, they force us to confront the strangeness of space-time. Because if nothing can truly be empty, and if black holes aren't the end of the story, then the universe might be far more dynamic and far more mysterious than we ever imagined. Black holes devour everything in their path, but what if the universe has a way of spitting things back out? Enter white holes, the theoretical antithesis of their dark counterparts. While black holes trap matter and light behind an event horizon from which nothing escapes, white holes are cosmic fountains, violently ejecting energy and matter into the universe in a one-way explosive flow. The equations of general relativity allow for such objects, but here's the catch: no one has ever observed one. They exist as tantalizing mathematical possibilities, cosmic what-ifs that challenge our understanding of spacetime. Imagine a black hole's mirror image, a region of space where matter can exit but never enter. Some theories suggest white holes could be the other end of an Einstein-Rosen bridge, the fabled wormholes of science fiction. Matter sucked into a black hole might emerge, transformed from a white hole in another part of the universe, or even another universe entirely. It's a poetic idea, cosmic recycling on a grand scale, where nothing is truly destroyed, just reborn in a new form. This leads to an even wilder thought. Could the Big Bang itself have been a white hole event? In bouncing universe models, where each cycle begins anew from a previous collapse, the moment of cosmic rebirth might resemble a white hole's explosive outburst. Picture a super-dense seed of spacetime, perhaps the remnants of a prior universe, rupturing outward in a fiery expansion, birthing galaxies from its energy. The symmetry is striking: black holes as cosmic endpoints, white holes as cosmic beginnings. Yet the mystery deepens when we consider dark flow, an unexplained phenomenon where galaxy clusters seem to drift toward a single point in space, as if tugged by something beyond the observable universe. Could this be the gravitational echo of a neighboring universe, or even the pull of a white hole's expelled energy? The data is controversial, but if confirmed, it hints at forces reshaping our cosmic neighborhood from unseen realms. From theoretical fountains of matter to the enigma of dark flow, the universe keeps revealing how little we truly understand. And if white holes are real, they might not just be cosmic oddities, they could be the universe's way of rewriting its own story, one explosive rebirth at a time. Galaxies aren't just drifting apart in the cosmic expansion, some are being pulled, as if by an invisible hand, toward something we can't see. This bizarre phenomenon, called dark flow, was first detected in 2008 when astronomers noticed hundreds of galaxy clusters moving in the same direction at staggering speeds, over 2 million miles per hour toward a patch of sky between the constellations Centaurus and Vela. It's not the expansion of the universe causing this, it's something else, something beyond the observable horizon. The simplest explanation: our cosmic neighborhood might be caught in the gravitational current of something massive, unimaginably massive, lying far beyond what our telescopes can reach. Picture standing on a beach, feeling the tide tug at your feet, but the ocean stretching farther than your eyes can see. That unseen ocean could be a supercluster of galaxies so vast, its gravity ripples across billions of light years, dragging everything toward it. Some theorists even speculated could be the gravitational imprint of another universe, a neighboring bubble in the multiverse pressing against our own. But not everyone's convinced. Skeptics argue dark flow might just be a measurement glitch, an artifact of how we map cosmic microwave background radiation, the afterglow of the Big Bang. Others suggest peculiar motions within our local supercluster could be skewing the data, yet the evidence persists. Later studies, like those from the Planck satellite, found hints of the same mysterious motion, though weaker. The debate rages on. Is dark flow a cosmic clue or a phantom in the data? Now, here's where it gets even stranger. Magnetic fields, those invisible lines of force weaving through space, might play a role in this cosmic tug of war. We've long known that galaxies are threaded with magnetic fields, some stretching millions of light years, powerful enough to shape gas clouds and steer cosmic rays. Could these fields be amplifying dark flow, acting like cosmic highways channeling galaxies in unison? Or might they be masking the true source of the motion, bending light and distorting our measurements? One thing's certain, the universe keeps reminding us how much lies beyond our understanding. Whether dark flow reveals a hidden structure, a flaw in our models, or something entirely unexpected, it's a humbling reminder that the cosmos is far stranger and far more dynamic than we ever imagined. And as we peer deeper into the void, we might just find that the answers rewrite not just our maps of the universe, but our place within it. Magnetic fields weave through the cosmos like invisible threads, pulling strings behind the scenes of galactic evolution. While gravity sculpts the large-scale structure of the universe, magnetism operates on a subtler scale, guiding star formation, channeling cosmic rays, and even imprinting order on chaos. Take the Milky Way. Our galaxy isn't just a swirling disk of stars. It's a labyrinth of magnetic fields, some stretching tens of thousands of light years, their forces strong enough to shape the paths of interstellar gas and dust. These fields aren't uniform, they twist and ripple, creating a dynamic web that astronomers can map by studying the polarization of starlight as it passes through cosmic dust grains aligned by magnetism. Where these fields are strongest, they become cosmic architects. In stellar nurseries like the Orion Nebula, magnetic pressure can resist gravity's pull, slowing the collapse of gas clouds and regulating the birth of stars. Without this braking effect, star formation might be a chaotic free-for-all, with massive stars burning out too quickly to ever seed planets or life. But magnetism doesn't just slow things down. It also accelerates particles to near light speeds, creating cosmic rays that spiral along magnetic field lines like beads on a wire. These high-energy particles, often originating from supernova explosions, can influence everything from Earth's atmospheric chemistry to the evolution of life itself. Now, zoom out even further. Some galaxies, like the majestic spiral M77, reveal magnetic fields so powerful they trace the entire structure of their spiral arms, as if the galaxy were sketched in luminous ink. Others, like the turbulent Centaurus A, show fields tangled by violent mergers, their magnetism twisted into knots by gravitational chaos. These observations hint at something profound. Magnetism isn't just a side effect of cosmic evolution, it's an active player, shaping galaxies as fundamentally as dark matter or gravity. This raises a startling possibility. If magnetism operates at every scale, from the tiniest plasma currents to the vast gulf between galaxy clusters, could the universe itself have a fractal-like magnetic structure? Fractals, those infinitely repeating patterns found in snowflakes and coastlines, might also describe the cosmos. Imagine magnetic fields replicating their geometry across scales, from the swirling eddies around newborn stars to the vast filamentary networks connecting galaxy superclusters. Some theorists suggest this could mean the universe is self-similar, with small-scale magnetic processes mirroring large-scale ones in an endless cosmic echo. From the delicate magnetic ballet of star-forming clouds to the grand, invisible arcs bridging galaxies, magnetism is a hidden force weaving order into the universe's fabric. And if fractal patterns hold the key, we might just be glimpsing the universe's deepest rhythm, one that repeats from the smallest spark to the largest structures in existence. The universe might not just be vast, it could be endlessly repeating like a cosmic hall of mirrors. This is the bold claim of fractal cosmology, the idea that the structure of everything from galaxies to galaxy clusters follows the same intricate patterns, no matter how far you zoom in or out. Picture a snowflake's delicate branches. Each tiny arm mirrors the whole, repeating its design at smaller and smaller scales. Now imagine that same principle applied to the cosmos, where clusters of galaxies form spirals within spirals and voids within voids in an infinite regress of self-similarity. The roots of this idea trace back to mathematician Benoit Mandelbrot, the father of fractal geometry. In the 1970s, he showed how nature, from coastlines to clouds, is filled with rough, repeating shapes that defy smooth Euclidean lines. When astronomers began mapping the universe's large-scale structure, they found something eerily similar. Galaxies clump into filaments and sheets, forming a cosmic web that looks uncannily like a neural network or a branching river delta. The distribution isn't random, it follows patterns that seem to echo across scales, as if the universe were a fractal artwork painted in starlight, but not everyone's convinced. Critics argue that while the cosmic web appears fractal-like, it doesn't truly repeat infinitely. Zoom out far enough, and the universe becomes smoother, homogeneous, a hallmark of the Big Bang's afterglow. The Sloan Digital Sky Survey, which mapped millions of galaxies, found that beyond a certain scale, the fractal pattern breaks down, giving way to uniformity. Some theorists counter that we simply haven't looked at large enough scales yet, or that dark matter's hidden scaffolding might preserve fractal behavior in ways we can't yet detect. This debate ties into something even stranger, the holographic principle. If the universe is fundamentally a projection of information encoded on a two-dimensional surface, then its three-dimensional complexity, including any fractal patterns, might just be an illusion, a shadow play of deeper, simpler rules. Like a fractal, a hologram contains the whole in every part. Shine light on a fragment, and you still see the entire image, just fuzzier. Could the universe's apparent self-similarity be a clue that we're glimpsing the edges of a cosmic code, where every galaxy, every atom, is a pixel in a grander design? From Mandelbrot's infinite twists to the hologram's hidden layers, the universe keeps hinting that its deepest truths aren't just complex, they're recursive, echoing across scales in ways we're only beginning to decipher. Two particles separated by billions of light years somehow remain linked, change one, and the other instantly responds, as if space and time don't exist between them. This is quantum entanglement, the phenomenon Einstein famously called spooky action at a distance. But what if this eerie connection isn't just a microscopic curiosity? What if it's woven into the fabric of the cosmos itself, binding galaxies and black holes in a hidden web of instantaneous influence? At the heart of this idea lies the ER equals EPR conjecture, a radical proposal from physicists Juan Maldaisner and Leonard Susskind. They suggested that entangled particles might be connected by microscopic wormholes, Einstein-Rosen bridges, threading through the fabric of spacetime like invisible stitches. Imagine two black holes, each containing an entangled particle. According to this theory, they wouldn't just share quantum information, they'd be physically linked by a tunnel through spacetime's hidden dimensions. It's as if the universe, to preserve the rules of quantum mechanics, warps geometry itself to maintain these ghostly connections. Now, scale this up. If entanglement can forge wormholes between particles, could the same principle operate across galactic distances? Some models suggest the cosmic web, the vast network of galaxies and dark matter filaments, might be held together by quantum links we can't yet detect. Picture two galaxies drifting apart due to cosmic expansion, yet still subtly entangled, their fates intertwined by threads of spacetime we're only beginning to comprehend. This isn't just theoretical poetry. It could explain why distant regions of the universe appear eerily synchronized, their structures aligned in ways that defy classical explanations. But how do we test such a mind-bending idea? Enter neutrinos, the universe's ghostly messengers. These nearly massless particles, born in the hearts of stars and supernova, stream through space almost undisturbed, barely interacting with matter. Yet they carry information across cosmic voids, potentially preserving quantum correlations over staggering distances. Recent experiments have hinted that neutrinos might exhibit entanglement-like behavior, raising the tantalizing possibility that they're part of nature's quantum network, stitching the cosmos together one invisible thread at a time. From microscopic wormholes to galactic-scale synchronicity, the universe keeps revealing layers of connection deeper than we ever imagined. And if entanglement truly shapes the cosmos, then reality might be far more mysterious and far more unified than our textbooks suggest. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace, their presence detectable only by the most sophisticated instruments on Earth. These nearly massless particles, born in the nuclear furnaces of stars and the cataclysmic explosions of supernova, barely interact with matter, yet they play a cosmic role far grander than their elusive nature suggests. When a massive star collapses, neutrinos aren't just bystanders, they're the driving force behind the explosion itself. In the final moments before a supernova, the star's core becomes so dense that even light can't escape, but neutrinos blast outward with unimaginable energy, carrying away 99% of the star's gravitational collapse energy in a single, devastating pulse. This neutrino shockwave is what rips the star apart, scattering heavy elements like iron and gold across the cosmos, elements that will one day become part of planets and even life itself. But neutrinos don't just destroy, they also build. Emerging from supernova at nearly the speed of light, these particles act as cosmic messengers, their paths unaltered by magnetic fields or interstellar dust. Some theories suggest they might even help seed galaxy formation, their subtle gravitational influence nudging clouds of primordial gas into the dense pockets that eventually ignite into stars. The sheer number of neutrinos flooding the universe, outnumbering atoms by 1,000,000,000 to 1, means their collective gravity could have shaped the large-scale structure of everything we see. Imagine a cosmic symphony where the faintest notes, barely audible, still somehow guide the entire orchestra. To catch these phantoms, scientists have built extraordinary traps. IceCube, a detector buried deep in the Antarctic ice, watches for the rare flashes of light produced when a neutrino finally collides with an atom. Other experiments, like Supermassive and in Japan, use vast tanks of ultra-pure water to spot the faintest ripples of neutrino interactions. These detectors aren't just hunting particles, they're piecing together the story of the universe's most violent events, from supernova in distant galaxies to the mysterious engines of active black holes. Yet for all their subtlety, neutrinos might hold clues to one of cosmology's greatest puzzles, phantom energy. This bizarre form of dark energy, even more enigmatic than the standard kind, could grow stronger over time, accelerating the universe's expansion to the point where galaxies, stars, and even atoms are torn apart in a catastrophic Big Rip. Some models suggest that neutrinos, with their ability to flit between different quantum states, might interact with phantom energy in ways we can't yet predict. If true, these ghostly particles could be whispering secrets not just about the universe's past, but its ultimate fate. From stellar explosions to the fabric of spacetime itself, neutrinos prove that even the most elusive things can shape the cosmos in profound and unexpected ways. Phantom energy isn't just another form of dark energy, it's a cosmic doomsday scenario waiting in the wings. While ordinary dark energy accelerates the universe's expansion at a steady pace, phantom energy is something far more sinister, a force that grows stronger over time, its grip on space-time tightening until reality itself unravels. Picture this: trillions of years from now, galaxies aren't just drifting apart. They are being ripped from their local clusters, stars torn from their orbits, planets shredded from their suns. But the horror doesn't stop there. As phantom energy's influence intensifies, even the fabric of space-time would stretch beyond its limits, snapping the bonds between atoms in a final, catastrophic instant known as the Big Rip. One moment the cosmos exists, the next nothing but a silent, infinite void. The timeline for this apocalypse depends on phantom energy's strength, but some models suggest it could happen in as little as 22 billion years, a blink of an eye on cosmic scales. First, galaxy clusters would vanish over the horizon, their light stretched beyond detectability. Then, individual galaxies would disintegrate as stars are flung into the darkness. In the last months, solar systems would dissolve. Minutes before the end, planets and stars would burst apart, and in the final fractions of a second, atoms themselves would be torn asunder, their nuclei and electrons ripped apart by the unstoppable expansion of space. It's a fate so violent, it makes black holes look gentle by comparison. Yet phantom energy raises a deeper question. What if dark energy isn't a constant at all, but a field evolving in ways we don't yet understand? Some theories propose that dark energy's strength could peak and then fade, like a cosmic fever breaking. Others suggest it might oscillate, driving cycles of acceleration and deceleration that could prevent a big rip entirely. The problem: our current tools can't measure dark energy's behavior with enough precision to rule out these possibilities. Every observation, from distant supernova to the cosmic microwave background, hints at something mysterious, but the data remains frustratingly ambiguous. This uncertainty has led some physicists to reconsider gravity itself. What if Einstein's theory of general relativity, while brilliant, is incomplete? Modified gravity theories, like Mund or scalar tensor models, tweak the equations to explain cosmic acceleration without invoking dark energy at all. Imagine gravity weakening over vast distances, causing galaxies to drift apart faster than expected. No phantom energy required. These ideas are controversial, often struggling to explain all observed phenomena, but they represent a thrilling possibility that the universe's fate might hinge not on an invisible force, but on our understanding of the most familiar one. From the nightmare of phantom energy to the radical rethinking of gravity, the universe's expansion isn't just a puzzle, it's a mirror reflecting how much we still have left to learn. And as we peer into that abyss, we might just find that the answers rewrite not just the cosmos's future, but the very laws we thought governed it. What if everything we think we know about gravity is wrong? For centuries, Newton's laws and Einstein's relativity have been the bedrock of our understanding gravity as the curvature of space-time, the invisible hand shaping galaxies and stars. But there's a problem. When we look at galaxies spinning, something doesn't add up. The outer stars orbit so fast they should fly off into space, yet they don't. The prevailing explanation: dark matter, an invisible substance adding extra gravitational glue. But what if the answer isn't hidden matter, but hidden flaws in our equations? Enter modified Newtonian dynamics, a radical idea that rewrites gravity itself to explain these cosmic anomalies without invoking dark matter. The premise is simple. At extremely low accelerations, like those in the outskirts of galaxies, gravity behaves differently than Newton or Einstein predicted. It's not that dark matter doesn't exist, it's that we might not need it. proponents point to stunning successes. Mund predicts the rotation curves of many galaxies with eerie precision, matching observations where dark matter models often require tedious fine-tuning. Take the Bullet Cluster, though a cosmic collision where visible matter and gravitational effects appear separated, as if dark matter were left behind. Mund struggles here, forcing its advocates to propose exotic additions like phantom dark matter, a workaround that starts to look suspiciously like the thing it's trying to replace. Yet the debate rages on. Some galaxies, like Dragonfly 44, appear to be almost entirely dark matter, with so few stars that Mund adjustments can't easily account for their gravity. Meanwhile, others fit Mund predictions like a glove. Could the truth lie somewhere in between? Perhaps gravity is modified, but not in the way Mund suggests, or maybe dark matter is real, but interacts in ways we haven't yet imagined. The stakes couldn't be higher. If Mund is right, it would upend a century of astrophysics. If it's wrong, why does it work so well for so many galaxies? Now shift gears to something even stranger: time crystals. These aren't sci-fi artifacts but real, bizarre structures where atoms move in repeating patterns, not just in space but in time. Picture a snowflake that doesn't just sit there but pulses rhythmically without energy input, forever cycling in a quantum dance. Normal crystals break spatial symmetry, their atoms arrange in grids. Time crystals break time symmetry, their patterns echoing at fixed intervals like a clock that ticks without being wound. Discovered only in the last decade, time crystals challenge our notions of equilibrium. Most systems settle into stillness. These never do, sustained by quantum entanglements, ghostly links. They're not perpetual motion machines. They don't violate thermodynamics, but they hint at a deeper truth. Time itself might have textures we're only beginning to perceive. Could the universe's fundamental laws allow for more exotic phases of matter, ones that ripple through dimensions we've yet to name? From rewriting gravity to redefining time, these ideas remind us that the cosmos is far from figured out. Every answer births new questions, and every assumption, even Einstein's, might one day bend under the weight of discovery. Time crystals defy everything we thought we knew about motion and equilibrium. Unlike ordinary matter, which settles into stillness when energy dissipates, these bizarre quantum structures pulse rhythmically forever, without any energy input. Picture a clock that ticks on its own indefinitely, not because it's wound up, but because the very fabric of reality allows it. First theorized by Nobel laureate Frank Wilczek in 2012, and later created in labs using chains of ions or diamond defects, time crystals are more than just scientific curiosities. They represent an entirely new phase of matter, one where atoms synchronize their movements in a repeating time loop, locked in an eternal dance governed by quantum entanglement. What makes them truly astonishing is how they break symmetry, not just in space like a snowflake's pattern, but in time itself. Imagine tapping a pendulum once and watching it swing back and forth perfectly, forever, without friction or decay. That's the essence of a time crystal, a system that resists the universe's relentless push toward disorder. In labs, researchers have observed this eerie behavior by using lasers to nudge particles into a non-equilibrium state, where they then oscillate at a fixed period, untouched by external energy. It's as if these crystals carve out a loophole in thermodynamics, dancing to a rhythm written into the laws of quantum mechanics. Now, stretch this idea to cosmic scales. Could time crystals have formed in the early universe when conditions were far more extreme? Some theorists speculate that the seething quantum foam of the primordial cosmos might have birthed natural time crystal structures that pulsed with the universe's first moments, imprinting their rhythms onto spacetime itself. If true, these relics could have influenced the formation of cosmic structures, perhaps even seeding the regularities we now see in galaxy distributions or the cosmic microwave background. It's a wild thought. The universe's large-scale order might trace back to microscopic clocks ticking in the void. This leads us to another enigma lurking in the early cosmos: primordial black holes. Unlike the stellar mass black holes born from collapsing stars, these hypothetical objects could have formed in the universe's first seconds, when dense fluctuations in the newborn cosmos collapsed under their own gravity. Ranging in size from a speck of dust to a mountain, they'd be invisible yet pervasive, weaving through space like ghosts. Some scientists even propose that primordial black holes could account for dark matter, their collective gravity shaping galaxies without emitting light. But here's the tantalizing link. If time crystals existed in the early universe, their rhythmic distortions of space-time might have triggered the density variations needed to birth these black holes. Picture a cosmic feedback loop: time crystals pulsing, space-time rippling, and black holes condensing from the chaos like droplets in a cosmic storm. It's a speculative idea, but one that bridges the quantum and the cosmic, suggesting that the universe's oldest mysteries might be written in the language of its strangest phenomena. From lab curiosities to cosmological architects, time crystals remind us that the universe's rulebook is far from complete. And if they're out there ticking silently in the dark, they might just hold the key to understanding how order emerged from the primordial frenzy and how reality itself learned to keep time. Primordial black holes aren't just hypothetical oddities. They could be the universe's oldest hidden architects, forged in the unimaginable chaos of the Big Bang itself. While most black holes form from collapsing stars, these ancient relics might have condensed directly from the dense, roiling energy of the early cosmos, when space-time was so tightly packed that random fluctuations could collapse into gravitational pits. Picture a universe less than a second old, hotter than the core of a star, where quantum ripples in the fabric of reality itself pinched off into microscopic singularities, some as light as a paperclip, others as massive as a mountain. Unlike their stellar-born cousins, these primordial black holes wouldn't be confined to galaxies. They could drift through the void like invisible icebergs, their gravity subtly tugging at everything they pass. This raises a tantalizing possibility. Could these ghostly remnants be the dark matter we've been searching for? If enough primordial black holes formed in that first explosive second, their collective mass might explain why galaxies rotate faster than visible matter alone can account for. Imagine a halo of these ancient objects surrounding the Milky Way, their gravity stitching stars together like invisible thread. The theory isn't without hurdles, though. Too many small primordial black holes would have evaporated by now due to Hawking radiation, the slow leakage of energy predicted by Stephen Hawking, where black holes shrink over eons, eventually vanishing in a final, faint burst of particles. But if some were just the right mass, say, as heavy as an asteroid, they could still linger today, hiding in plain sight. Hawking radiation itself is a cosmic irony. Black holes, the ultimate consumers, aren't entirely black. Quantum mechanics allows particles to escape their grip, stealing tiny amounts of energy in the process. For a primordial black hole the size of a proton, this evaporation would be explosive, ending its life in a flash of gamma rays. Some scientists even hunt for these telltale bursts in the cosmos, potential fingerprints of the universe's tiniest and most elusive predators. Yet the story doesn't end there. If primordial black holes are real, they might be weaving a darker narrative about the universe's fate. As space expands and matter thins, these ancient objects could outlast everything: stars, galaxies, even protons themselves. In a future so distant it defies comprehension, they might be the last structures standing, slowly dissolving into Hawking radiation as the cosmos fades toward absolute zero. It's a haunting thought. The universe's first creations could also be its last witnesses, silent sentinels watching as time itself unravels. From explaining dark matter to scripting the cosmos' final act, primordial black holes remind us that the answers to our biggest questions might lie in the smallest, most forgotten corners of creation. The universe could end not with a bang, but with a whisper, a slow, inexorable fade into darkness known as heat death. Picture a cosmos where every star has burned out, every black hole evaporated, and all matter itself has decayed into faint radiation drifting through an ever-expanding void. Temperatures approach absolute zero, chemical reactions become impossible, and time itself loses meaning in a universe where nothing changes, nothing happens, just an endless, silent stillness stretching into eternity. It's the ultimate triumph of entropy, where even the energy to fuel thought ceases to exist. This isn't science fiction. It's the most statistically likely fate of our universe, dictated by the relentless laws of thermodynamics. But what if death isn't the end? Some theories suggest the universe might have an escape clause, a cosmic reset button hidden in the fabric of reality itself. Take vacuum decay. Our universe's current state might be a false vacuum, teetering on the edge of a more stable configuration. If a tiny patch of space were to quantum tunnel into this lower energy state, it could trigger a bubble of destruction expanding at the speed of light, rewriting the laws of physics as it goes. One moment, reality as we know it exists. The next, an entirely new universe with different constants and forces blooms in its place. It sounds apocalyptic, but here's the twist. The new physics inside that bubble might allow for fresh cycles of star formation, galaxies, even life, a rebirth within the ashes of the old cosmos. Then there's the possibility of a new Big Bang, not from a collapse, but from a quantum fluctuation in the void. In a universe that lasts forever, even the statistically impossible becomes inevitable. A random quantum event could conjure a new inflationary bubble from the endless nothing, birthing a fresh cosmos with its own laws and wonders. Imagine a cosmic hourglass where each grain of sand is a universe, tumbling one after another into existence. Our universe might just be one link in an infinite chain, each ending seeding a new beginning. Cycles of destruction and creation aren't just poetic, they're written into the math of string theory, loop quantum gravity, and even the holographic principle. The universe might be a phoenix forever rising from its own demise. Whether it's heat death's cold silence or the fiery promise of renewal, one truth remains: the cosmos is far more dynamic, far more mysterious than we ever dreamed. And as we peer into the abyss of time, we're left with a humbling thought: endings aren't always final. Sometimes they're just the start of a story we've yet to tell.